15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again and welcome. Thank you for joining us on Space Nuts. It's all about astronomy and space science, and sometimes it's about animals because they interrupt us from time to time. My name is Andrew Dunkley, your host, and today we've got a lot to talk about. A shameless self-promotion by Fred Watson about a particular new book. We're also going to talk about a new exoplanet. Now, we've found thousands of them so far, but interestingly, they've all been in our galaxy until now, perhaps. We'll talk about that. There was a mystery signal identified late last year. We think we know what it is, and it's not very exciting at all. Could be a broken microwave. Now, we'll have to tell that story now that I've mentioned that. And we're going to tackle 3 audio questions today, one on dark matter. Shocker. Another that I found most interesting, though, about niche locations where we could live if we ever had to leave Earth, or maybe if we want to expand, when Earth's just too small for how many people there are. And asteroid mining. That's all coming up on this edition of Space Nuts. And joining me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew. How's it going? How's it going over there in Dubai?
Well. It's going very, very well, yes. Enjoying freedom after all that lockdown stuff.
Yep.
And funny thing is, Judy and I went out on Sunday to do a bit of shopping on the other side of town where we haven't been for over 2 months. And we drove through an intersection that's been rebuilt and we didn't recognise it. Yeah. And a petrol station has turned up that that wasn't there before. So it's just really weird. And it's a couple of kilometres away. So it's not far down the road, but we just haven't been able to go anywhere near that. So it's been bizarre. I'm sure other people have experienced similar things. Now, Fred, we've got a lot to tackle today, but first of all, Space Warp.
Yeah.
Space Warp, the book.
The book, Space Warp, the book.
Has that been officially launched now?
Not until next Monday, the 1st of November. That's when it comes out. It's got words on the back as well, including some very nice...
costs extra.
Well, yeah, there's some very nice endorsements by some famous people, including the founding head of the Australian Space Agency, Megan Clark, and the Astronomer Royal for Scotland, Catherine Haymans, Dr. Carl, who you will know of, has written something nice, as has Alan Duffy and Libby Gleeson, who's a famous children's author. And this is a book for young people. That's why Libby has played her part.
Oh, nice. Yeah. Note well, I was not asked.
Well, look, it's not me who does this. It's the publisher. They just pick the people.
I don't care.
No, the publisher.
I wouldn't have said anything nice anyway, Fred.
I'm going to throw in another bit of self-promotion, Andrew, because alongside the book, there is the calendar, the 2022 Space Warp calendar, which
look at that.
is because the book's full of my cartoons, and there's lots of them in there.
You do your own
calendar, things like that.
Wow.
So, yes, that will, we hope, be available. Both of them will be available via the Space Nuts website, Space Nuts podcast website.
Yes, we've got a Space Nuts shop on our website, so we'll make sure that they're available there. So we'll let you know when they'll pop up, but it won't be long. But yeah, congratulations, Fred. I know you've been working hard on that, and it's very exciting news indeed. So can't wait to get my free copy.
You will.
No,
you'll get one. Don't worry. You're on the list.
Yes, right at the bottom. All right. Yes, it's called Space Warp, by the way. It's a book about astronomy for young people. So, if you've got a budding young astronomer or space traveller in the family, there you go. It could be for them. Now, speaking of space travellers, we are, it's not so much about space travel. It's about observing beyond our locality in space. And that is a new exoplanet. Now, to date, we've found several thousand of them, and we continue to find them through the various techniques. But this one is different. This one may well be the first exoplanet discovered beyond our galaxy. Now, most people will probably say, well, yeah, that's no surprise. We should expect that. But still, pretty exciting to be the first one, if that's the case.
It is. There's a lot of media hype around this story, Andrew.
I know.
And it probably isn't the first one. There've been other candidates. The thing is, detecting a planet of a star in a different galaxy is a monumental achievement. It is such a big thing. It's hard enough to find them in our own galaxy, and all the ones that have been found are probably within, I don't know, probably within a few hundred thousand. Not even a few hundred thousand, a few tens of thousands of light years away. There's some evidence of exoplanets in the region of the galactic center, which is about 27,000 light years from our solar system. So that's the sort of range that we're talking about. But when you get to galaxies, you're talking about things that are millions of light years away, and often billions. And let me sort of set the record straight a little bit, because there have been candidates for extrasolar planets, in extragalactic systems. In other words, galaxies beyond our own. There are already about 3 or 4 candidates for these, and of course, the difficulty is how do you prove it? So I would preface this story with that note of caution that it may well not be the first, but it's certainly a notable achievement, and it's a really interesting observation as well. It's of an object. So let me tell you that this has been detected by the Chandra X-ray telescope. It's not visible light telescopes that have picked this up, but a telescope that observes at X-ray wavelengths. And Chandra is a NASA observatory, the sort of X-ray equivalent of the Hubble Space Telescope. What they've done, the astronomers, they've been looking. Actually, I think they've looked at several relatively nearby galaxies, including M51, Messier 51, which is often called the Whirlpool Galaxy, because that's what it looks like. And that's about 28 million light years away, meaning it's 10 times further away than the Andromeda Galaxy, which is our nearest big galaxy. So it's quite a way off. But using the X-ray observatory, what they've been doing is looking at the X-ray signal from basically binary systems which contain highly condensed objects, by which I mean a neutron star or a black hole or both. It's usually the kind of scenario that we've got, and this is the way that most X-ray objects in the sky shine in X-rays. You've got something like a neutron star or a black hole with a companion normal star going around it. And the gravitational pull of the neutron star is pulling stuff off the companion, and it's basically that material whizzes around the neutron star or black hole. It gets highly heated and glows in X-rays. But now here's the trick: that region where the X-rays are produced is very small. And if you had a planet that was in orbit around one or both of these objects, the star or the neutron star or the black hole, whatever it is, if you have a planet in orbit around it, that planet could block off most of the X radiation coming from that small source of X-rays because of the superheated gas. And it makes available the transit method, the standard transit method, which is what we use in our galaxy, where a star passes in front, a planet passes in front of its parent star. We see a dip in the light, which has a very characteristic shape in its light profile. And that demonstrates that there is a planet in orbit around the star. And usually what you have to do is watch this for several transits. I think 3 is the minimum before you can guarantee that you've found that you have found a planet. This is slightly different because the X-ray source, unlike the parent star of a planet in our galaxy, which is much bigger than the star, so all you get is a dimming of that star's light. I beg your pardon. It's much bigger than the planet. I'm sorry. Get the words right. The star is much bigger than the planet in our galaxy. And so as the planet crosses in front of the star, it's like the starlight merely dims. But with this situation, the X-ray source is smaller than the planet. And so when the planet passes in front of it, it basically switches off the X-rays.
Wow.
And then they come back on again.
Yeah.
So there is a known X-ray source in M51, the Whirlpool galaxy. Its name is M51 ULS1, and that is either a black hole or a neutron star with a companion star, which is about 20 solar masses, and that basically is what causes the bright X-ray emission. So all that's been modelled from the X-ray emission. But now what you've got to do is monitor this and look for a planet or something blocking it off. And that's what they found. It's basically a dimming of the light. It lasted about 3 hours when the X-ray emission fell to 0. And so that's what they are interpreting as a planet around M51 ULS1. And they guess it's about the size of Saturn and think that it would orbit the black hole or the neutron star about twice as far away from the neutron star as Saturn is from the sun. Right. The really depressing bit, Andrew, is that based on those calculations, the next time it's going to block out the light of the X-ray source is in 70 years. So we've got a long wait before you can actually guarantee that this is definitely a planet.
That's frustrating.
Yeah, very frustrating. It's been, other people have suggested maybe it's actually a cloud of gas and dust that's passing in front of the X-ray source. They say that the characteristics of that dimming of the light or the X-rays from M51 ULS1 is more consistent with a solid object like a planet. There's a very nice comment by one of the authors who's at Princeton University in New Jersey. We know we are making an exciting and bold claim, so we expect that other astronomers will look at it very carefully. This is Julia Berntzen. She says, we think we have a strong argument, and this process is how science works.
Yeah. It must be frustrating when you find something and then realise you're going to have to wait 140 years to get an absolute confirmation.
Yeah, that's right.
I dare say we'll find other candidates before that happens.
Yeah,
but
I think we might.
Why is it so difficult to confirm an exoplanet in another galaxy? Is it because when we look out, everything's just conglomerated into one mass?
Yeah, well, that's partly it.
Telling one from another is the issue.
Yeah, so that's why you've got to. So if you were just looking at straightforward stars, you wouldn't have a chance because at the distance of M51, the bright ones will show up individually, but most stars just melt into a haze, a bit like the way we see the Milky Way, that haze of starlight. But X-ray sources are different. First of all, they're relatively rare within a galaxy, so you can pick them out easily because they are so bright in X-rays compared with the background from the galaxy itself. There's probably other aspects. I'm not that cluey about the details of X-ray astronomy, but I think it's likely that you would be looking for a different region of the X-ray spectrum for the kind of observations that we're talking about here from the what we call the extragalactic X-ray background, things of that sort. So it's a difficult task, and that's why you need something really extraordinary like an X-ray source and a tiny X-ray source, which is what this is, in order to have some evidence of a planet there. Yeah,
well, hopefully, but yes, as we've mentioned, it'll be a while before we can
for this one. That's
properly
right.
confirm it. But yes, look, logic says that there are probably squillions of exoplanets in other galaxies, just like there are in our galaxy. We've got planets around our star. We've found planets around many other stars in our galaxy. It stands to reason that the pattern repeats.
Yes, that's right.
So one day soon, I'm sure, we will confirm an exoplanet in another galaxy, and everyone will go, yeah, we thought that'd be there. It'll be exciting, but it'll also be expected. That's how I anticipate it going. So, and yeah, as you said, we've probably already discovered them. We just can't absolutely confirm it yet.
That's right. There are other candidates that come from things like gravitational lensing or gravitational microlensing and things of that sort.
Yes.
Yeah.
Yes.
Yeah.
All right. We wait with interest.
We do.
Of course. Can't afford the interest, but we're going to do it anyway. You're listening to Space Nuts, and you're watching us on YouTube if you choose to, where you can see the cover of Fred's new book, which he just showed us if you want to take a look at it, with Andrew Dunkley, of course. There he goes again. And Professor Fred Watson.
Roger, your labs are here also.
Space Nuts.
Now, Fred, before we move to our next topic, I got a lovely email this week and basically asking for help. And I thought, well, yeah, why not? Let's give them help. Hi, guys. I'm an avid listener of your podcast and have just started working in marketing for the University of South Australia Innovation and Collaboration Centre based in Adelaide. And that's where they run the Venture Catalyst Space Program, which he tells me is a 6-month startup incubator for local and international companies in the space sector with the support of the South Australian Government Space Innovation Fund. And right now, this is from Daniel, he tells me that they're accepting applicants for the 2022 program. Now, that closes on November the 28th. And he was hoping we could mention it to our listeners and maybe get that message out to people who could take advantage of this wonderful opportunity. So there you have it. If you're interested in this 6-month program, for companies in the space sector, get in touch with the University of South Australia's Innovation and Collaboration Centre based in Adelaide and see what you can do for their 2022 program. I'm sure Daniel will be excited to hear from you. And you never know where it might lead. So good work, Daniel. Thanks for getting in touch. More than happy to give you a little plug on that program and wish you all the very best. And please stay in touch. Let us know how it goes. Sounds fantastic. Adelaide's becoming quite a centre for space in Australia, isn't it, Fred?
Very much so, yes, with the Space Agency having its headquarters there. And South Australia, of course, has a long history of space activities going back to the Woomera days. And they've picked up all that again with this new wave of investment in space projects.
I still love how we have sort of taken in the space program in Australia, and our very first rocket still lies on its side, rusting behind a chicken wire fence. I think that is that just underlines it for me. In terms of Australians' space, I think we'll improve on that.
Maybe.
What's more, it was an American rocket and the kangaroo burnt off, so you can still see the American USA underneath. I think that's hilarious. Let's move on.
All right.
Now, last December, there were media reports of a mystery signal that we've been trying to unravel, and it came from a place that sort of got people scratching their heads. Well, now we think we know what it is. Over to you, Fred.
I might actually read what I wrote about it in this book, because I wrote about this. In December 2020, reports emerged that a signal had been detected at the Parkes Observatory in New South Wales in 2019, 3 years into the Breakthrough Listen project. That's a project to listen for extraterrestrial signals. Dubbed BLC-1 for Breakthrough Listen Candidate 1, the signal came from the direction of the nearest star, Proxima Centauri. Scientists are still working to identify its origin, but comment that it is 99.9% likely to be human-made interference of some kind. So I wrote this about 3 months ago, and now they've agreed that it is.
Yeah.
All the pundits that I spoke to said, look, it's got to be human interference. But there's a little bit more to the story. The signal had all kinds of similarities with what you might expect an extraterrestrial signal to look like, and in fact, people have been looking with the Parkes Radio Telescope at Proxima Centauri for a long time because it's a flare star. It flares out bursts of energy like our sun does, but because it's a red dwarf star, they're much more energetic. And so it's one that has been studied. We also know that Proxima Centauri has in orbit at least one Earth-sized exoplanet, and the suggestions here that that planet is, in the same way as the Earth experiences space weather from the solar flares, the space weather around Proxima Centauri B, that's the name of the planet, is pretty energetic. And I think most pundits think that would rule out the evolution and development of life. But yeah, it's the nearest neighbour. It's an object that's very easy to observe from our southern skies. And so the Breakthrough Listen team have essentially concentrated a little bit on Proxima Centauri. And sure enough, this signal came in. It reminds me a lot, Andrew, of the WOW signal that nobody wrote WOW. But the reasons why the signal could be artificial have been listed in a very nice conversation piece by Danny Price, who's one of the authors. He's at Curtin University in Western Australia. So Danny lists the things. His conversation piece, if you want to look at it, is called "A Mysterious Signal Looked Like a Sign of Alien Technology, but it turned out to be radio interference." That's telling it like it is. What Danny says is that they only saw BLC-1 when they were looking towards Proxima Centauri and didn't see it when they looked elsewhere in what are called off-source observations. Whereas normally interference leaks into the telescope from everywhere. So that was one thing. Second point is that the signal it only covers one narrow band of frequencies. And, natural astrophysical sources are usually over a much wider range. Normally, clouds of cold hydrogen aren't, but normally you would get a much wider range. And the thing that really made it intriguing was that the signal drifted in frequency over a 5-hour period. And that's sort of what you would expect from a signal coming from a planet orbiting another star because of the Doppler effect. You get this Doppler shift because of the relative movement between the Earth and the star. Actually, the Earth's movement as well contributes to that. And it persisted for several hours. That's what they said. However, they have demonstrated, and I think it's a summer project that was being done by a PhD student, Sophia Sheik, I think is the name, the way her name is pronounced, a PhD student at Penn State in the USA, who ran lots and lots of tests, which have basically what has thrown out the techno signature idea, that which is of course a signature coming from a technologically advanced society. She has done this by going across the Parkes receiver's complete frequency range and actually found lookalike signals that are similar to BLC-1, which do appear in off-source observations. And so it suggests that it's actually some sort of peculiar radio interference. And what they're saying, and this is me quoting directly from Danny's article, we don't know exactly where BLC-1 was coming from or why it wasn't detected in off-source observations like the lookalike signals. Our best guess is that BLC-1 and the lookalikes are generated by a process called intermodulation, where two frequencies mix together to create new interference. If you've listened to blues or rock guitar, you're probably familiar with intermodulation. I have to say, when I'm playing blues guitar, I don't intermodulate, Andrew, as you'd expect, mainly because I don't use an amp. I'm purely acoustic. When a guitar amp is deliberately overdriven, i.e. when you turn it up to 11, intermodulation adds a pleasant sounding distortion to the clean guitar signal. So BLC1 is perhaps just an unpleasant distortion from a device with an overdriven radio frequency amplifier.
Well, that's disappointing.
It is, isn't it?
But not unexpected. It reminds me of a story, and I can't remember the details, but some years ago there was some kind of discovery made, and then they eventually figured out it was like a broken microwave oven.
Yes.
Do you remember that?
Yeah, it wasn't broken. And this is Parkes as well.
Right.
Yeah, so this was in the early history of the detection of fast radio bursts, which are signals that last a few milliseconds, which are now generally thought to be coming from flares on neutron stars. I think that's the consensus these days. But in the early days, nobody had a clue what they were. And they found a whole succession of these signals, exactly like the what we might call the classical fast radio bursts, from the Parkes radio dish. They had this same intensity profile. They had a phenomenon called dispersion, which is actually something that happens to radio signals as they pass through space. The low frequency signals, let me get it the right way around. I always get this the wrong way around. I think the lower frequencies come last. They do, they're slower. So that's dispersion as they pass through space. And these signals at Parkes mimic that. They had the dispersion. So everybody thought they were natural, except for one thing, cosmic, coming from space. Excuse me, except for one thing, which is that they all always turned up at lunchtime. And anything that comes up on a period of 24 hours must be something to do with the Earth. So they started then looking at nuclear tests and jet aircraft interference. And it took a long, long time. And I've talked to one of the guys who actually discovered what it was, John Sarkisian, a great friend and colleague at the Parkes dish.
Yeah.
What it turned out to be was people, I should say, they ran tests on all the microwave ovens in the district, and nothing that turned them on and off and everything, not got anything that resembled this thing. And I should say they gave it a name. They called them peritons, which is a fictitious animal invented by an Argentinian a fiction writer. So the peritons it turned out to be caused when somebody's cooking a meal, and they think that the cooking's done enough, but the microwave's still running, and they press the door open button, and it cuts the microwave, but it lets the radio radiation, as it decays, expand into space.
That's
and
hilarious.
They did several tests, and that's what it was. I think it was John Reynolds as the person.
So that's what would happen, where it's finished cooking and it's giving you the 5 warning beeps, or however many it is, and you open the door before the beeps stop.
It's more
the radiation's escaping. It's
more that you say, you're looking through the window and you've got 5 minutes on the timer, but after 3.5 minutes it's cooked, and you press the door open button then. So the magnetron is still generating the microwaves. The door opens, the microwaves escape into space, and they've got this frequency drop exactly as you'd expect. So
that's what it was.
Yeah.
That's amazing. And it's not advised either, is it? We shouldn't do that.
It's very naughty. That's right. And so it's now forbidden at Parkes.
Which is why it gives you the warning beeps. Don't open the door till the beeps stop. That's what that's all about. It's not to tell you your food's cooked.
That's right. Yes. Leave it up until the beeps stop.
Another important safety tip from Space Nuts.
Indeed. Yes. Look after your microwave.
All right. So the mystery signal, not such a mystery. Not a microwave oven thing, but certainly some kind of interference.
Some sort. That's right.
Yes. All right. This is Space Nuts. You're with Andrew Dunkley and Fred Watson.
0G, and I feel fine. Space Nuts.
Now, if you are on social media, particularly Facebook, don't forget we have a couple of pages. We've got the official Space Nuts Facebook page, which you're more than welcome to join and to follow. But we also have a listener-created Facebook page, which we administer, but it's basically driven by the listeners, and it's the Space Nuts Astronomy Science Podcast Group. But if you do Space Nuts Podcast Group in your search engine on Facebook, you'll find it. And that's where well over 2,000 listeners now get together regularly to talk astronomy and space science. They ask questions of each other. They come up with theories and answers and ideas. They share photographs. Some people are sharing their astrophotography, which is fantastic. And you can be a part of that group just for the fun of it. And you can, I just spotted a message from my brother there that said, "Oh my God, Andrew, did you tell your Space Nuts listeners about the jet engine under Paul's place that caught fire?" Yes, I did. Yes. It's all on the Space Nuts podcast group on Facebook. So check it out. It's a fun place, and it's for you. We don't get very involved. I might occasionally drop in a comment, but it is for you, so you can talk to each other. All right, Fred, let's tackle some questions. Oh, good grief, shock horror. This one's about dark matter.
Hello, Andrew and Fred. This is Michael in Evanston, Illinois, in the United States. I have a couple of questions about dark matter that mainly relate to Einstein's famous equivalency principle with respect to matter and energy, the E equals mc squared formula. Is there a process that we know of that converts dark matter into energy, like, for example, around a black hole? Is dark matter part of the matter that results in the terrific energy that's released? I think that's it. Thank you. Love your show. Take care.
Okay, you too. Michael, thanks for the question. Lovely to hear from you. So basically asking if there is a process that converts dark matter into dark energy. Is that what he said?
No, that converts dark matter into energy.
Into energy.
Yeah. In the same way that, the nuclear processes inside the sun convert matter into energy. But in that case, it's normal matter. That's a really good question. I might just start with a comment from Pedant's Corner, which is where all astrophysicists sit. Einstein's equivalence principle is not about matter and energy. It's not about E equals mc squared. It's actually about something different, and it's what led to the general theory of relativity. It's the equivalence of gravitational and inertial mass. In other words, that it's the thing that leads to the idea that gravitation behaves like an acceleration. That's the equivalence principle, I think formulated in, if I remember rightly, I think he thought of it in 1907 and formulated it in 1912 in its detail. But it was in 1905 that E equals mc squared was written down. That's the equation that, exactly as Michael says, relates the mass of an object to its energy content. That's the best way to put it. And you and I have discussed some of the few instances of converting it the other way around, going from energy to matter, which can happen in particle accelerators, I believe. That's in the past when we've talked about this, Andrew. But it's a really intriguing idea that are there processes like nuclear fusion, for example, or nuclear fission, that relates to dark matter and energy? And I'm not sure what the answer is to that. My guess is that there may well be. The reason why I say that is that people have put forward suggestions that if you have dark matter particles colliding, they can annihilate, and what you get is gamma rays. And in fact, people have looked for gamma rays with a particular spectrum profile coming from the centre of our galaxy, where we think the dark matter is at its densest, and that's where you would expect dark matter particles to collide and release these gamma rays. So that would be an example of exactly what Michael is suggesting, the conversion of matter to energy, albeit dark matter, something that we only see through its gravitational interaction. But so far, there haven't been any detections of gamma rays with the particular profile that would be expected from annihilating dark matter particles.
Okay, so the mystery continues.
It does.
All right. Thank you, Michael. Again, lovely to hear from you. Let's move on to a question from Patrick.
Hello, Andrew and Dr. Fred. My name is Patrick, and I live in New England in the USA. I was wondering if there are niche locations in the solar system that would be Goldilocks locations. For example, the poles of Mercury, where the one side is very hot, the other side is very cold, but it would be possible to live in between them and use the temperature difference to power all kinds of things that are needed for life support. I'm also thinking of the same thing in other places. So if you could just go through the solar system and tell me where people might be comfortable, that would be great. Thank you.
Interesting. Yeah, that's a good thought. Obviously, Earth is perfect. It's it's not, but in terms of liquid water position in the solar system, distance from the sun, everything about it just falls into place for the proliferation of life, and we can walk around freely and breathe the air and drink most of the water, some of the water. But if we were to move somewhere else, we would have to find niche locations that would be amenable to a reasonable existence. How do we find them, and are there any that are, the way he describes?
Well, you're right, Andrew, that the Earth is perfect. That's because we evolved here.
Yes.
And there's nowhere else that's got the same atmospheric pressure and chemical compositions in its atmosphere, as well as the right gravitational force and the right temperature. I think what Patrick's referring to is what we call the Goldilocks Zone, the idea that there is a region around every star where the temperature is not too hot, not too cold, but just right for liquid water to exist. And that is where we sit in our solar system. But yes, niche Goldilocks zones. I think Patrick's right about the terminator region of Mercury. That will be an area where the temperature, the radiative heat from the sun would make for a more benign surface temperature than either the sun-facing side or the dark side. The trouble is, of course, Mercury does rotate on its axis, albeit slowly, and that position changes. But that would be, I guess, one example of the kind of Goldilocks zone that he's thinking about. Perhaps a more interesting one, though, is the upper atmosphere of Venus, where Venus's surface temperature is 460 Celsius or something. But when you get high in the cloud deck, both the pressure and the temperature become much more amenable to life forms. And that's why there was all that excitement last year about the detection of a supposed radio signal from phosphine in the atmosphere of Venus, because phosphine is a bit of a biomarker. It's not a guaranteed one, but it's got a suggestion. In fact, that has now gone away. I think the signal turned out to be probably, was it carbon monoxide, I think, rather than phosphine. Anyway, it's one of those things. It's still a bit controversial, but it's it was thought to be perhaps the first signs of life in the upper atmosphere of Venus. We don't think that's the case now, but the fact remains that Venus's upper atmosphere may have conditions which would be suitable for life. When you look elsewhere in the solar system, once you get beyond the Earth, then you're outside the traditional, or the classical, if I can use that word again, Goldilocks zone, because when you get to Mars, it's only infrequently that you can find temperatures on the surface of Mars where liquid water could exist. And the problem there is the pressure is so low, the atmospheric pressure is so low that it just tends to evaporate. I was thinking, though, slightly outside the box. Jupiter's moon Io has lava lakes. The heating of Io comes from the tidal forces exerted on it by Jupiter. And so you could regard Io perhaps as a kind of quasi Goldilocks zone. And it may well be that we've got these water worlds out there as well with a layer of ice over a liquid water ocean, over a sort of warm rocky core. Maybe in those oceans there are temperatures that approach the temperature at which living organisms could form. It's the internal heating and the pressure of the ice above that gives rise to the fact that the water is still liquid. It's probably still very cold, below what we would normally think of as freezing point. But if there are minerals in there like perchlorates that act as natural antifreeze, plus this pressure effect reducing the freezing point, maybe there are creatures that could survive those conditions. So
fascinating.
Yeah, probably a few niche places. A good question, though.
Yeah.
Thanks, Patrick.
Not so good for humans, though. But while you were talking, I was looking down at a book I read recently by Kim Stanley Robinson called 2312, and it had a human colony on Mercury, and they lived in a city called Terminus, I think, and it was on a rail, and the rail got expanded by the heat of the sun, and pushed the city along around the planet. And they were always just on the shadow side of the terminus.
That's fantastic.
Or the Terminator. Yeah. And the city just got pushed around and around and around the planet, and everyone lived happily in the Goldilocks zone of Mercury. So that's how Kim Stanley Robinson solved the problem.
Very good.
But, it's an interesting puzzle. So, if we do ever have to move, we will have to be ingenious about it, that's for sure.
Yeah, we're likely to move the other way, though, aren't we? As the sun gradually expands into its red giant phase, we're going to be...
Yes, we definitely need to go the other way.
Yeah. So,
yeah. Hopefully by then, if humanity still exists, we'll be able to go beyond our own solar system and perhaps beyond our own galaxy and get out there and find something like Earth that would be worth living on. There's got to be one somewhere, surely.
You would think so.
Time will tell, but maybe not in our lifetime. All right, one final question. We'll throw in a bonus question today. I'm not sure who this is from, but I know they're in Melbourne.
Hello, Fred and Andrew. I just finished listening to your latest All Questions episode, and I thought I really need to get my own question in before singing becomes the norm, and I am forever excluded due to my musical ineptitude. I'm curious about the orbital dynamics of asteroid mining. Moving rocks just to mine out a tiny proportion of their contents is very expensive, and if you do it in space, even more so. Why not crash a bunch of asteroids into the moon and mine the fragments we want? Friend of the program 16 Psyche comes to mind. Can we cheaply and reliably knock 16 Psyche off its orbit in such a way that it will graciously impact the moon? Or would we vaporize all the interesting stuff? Would it be better to make it enter low Earth orbit? Can it be done safely? Thanks a lot. I love the show, and it has made all of Melbourne's lockdowns, all 6 of them, so much more bearable. Greetings from south of the border.
Lovely to hear from you, and so pleased that you're out of lockdown now, I believe, or very soon. And yes, the most locked down city in the world, as it turned out. So yes, it must be an incredible relief to be out of jail. Could we crash 16 Psyche or any other asteroid into the moon by glancing it off its current path and then mining the refuse? Is that feasible? Is it a good idea to crash stuff into the moon?
No, it's not.
I mean, we've done it with spacecraft, let's be real, but something as big as an asteroid?
Yeah. Yes, so 16 Psyche, one of my favourite asteroids, because I did research on its orbit when I was a master's student 100 years ago. We now know it's a metal asteroid. We know it's 200 kilometres in diameter, and there's absolutely no way that with present technology we could move that from its orbit in the main asteroid belt. Far too massive. There have been suggestions for moving small asteroids, and we're talking now about objects maybe a few meters across, which might still be rich in rare earths and perhaps metals and other minerals. That was discussed probably a decade ago, about the time when NASA was, talking about retiring the space shuttle and what they were going to do next. Moving asteroids around was one of the things that was thought to be a good idea, with the possibility of mining them. Now, the thing about mining asteroids is that for most of the stuff that's on it, the place you want to use it is in space. You don't really want to bring it back to Earth or crash it into the moon. You want to do what's called ISRU, in situ resource use. It's a pretty big iconic term that's appearing now in things like the Space Agency's roadmap here in Australia, and I think that's really the way the space industry will be going. It'll be looking at things like remote mining of asteroids, 3D printing using the materials that are excavated, and 3D printing things like rocket components, as well as electrolyzing some of the water ice that might be found into rocket fuel, all done in situ rather than bring it back to Earth. There is a mission about to be launched, just talking about moving asteroids.
The DART mission.
Is it DART? Yeah, this is the one.
DART, yeah, the double asteroid redirection test.
That's it, yeah.
Yeah, it's a NASA plan to go up there and try and deflect an asteroid, 65803 Didymos.
That's the one.
Offline.
Thanks for checking up on that. No, it's because it's a double asteroid. It's a binary asteroid. And the idea is to accelerate one component, the satellite, whose name I can't remember, the satellite asteroid, deflect that by a small amount, just to give it a tiny acceleration, and see what happens. Because we haven't, this is technology that we might need one day to move the orbit of an asteroid that threatens the Earth, which is a much bigger issue, and it's never been tested. So moving the asteroid's moon, or accelerating it by even a few millimeters per second, that would be an achievement. Why are they doing it with a binary asteroid? Because that's the easiest way to measure if you have generated the acceleration that you're looking for.
Yes, they're using the DART spacecraft and the Draco, the Didymos Reconnaissance and Asteroid Camera for OpNav, which is an imaging instrument, so they can see whether or not they were successful.
Whether it works, that's right.
And whether or not they'll be able to actually move this asteroid, and it's a very important test for keeping the planet safe from a potential future impact. So we're really only in the very early stages of testing this kind of science. So deflecting objects to hit the moon, or which Fred and I agree on is probably not a good idea. It's way beyond our science at this point in time, but we're working on it, but more for the safety of the planet than for the mining industry.
Yeah. And in fact, the last question, sorry, Andrew, to interrupt, the last question about could you put 16 Psyche into low Earth orbit, I think that would be catastrophic for human life on Earth if we did that.
Okay. So another important safety tip on space: do not put asteroids into orbit around
big ones like that. No.
No, not on your life. Well, you probably wouldn't have a life after that. But yeah, thanks for the question. No, it's a really interesting discussion. It always throws up some amazing thoughts. And thanks to everyone who contributed to the program this week. It brings us to the end. By the way, if you do have questions for us, you can always send them to us via our website, spacenutspodcast.com. There's a little AMA link on the top where you can send us email questions or record a voice question, or you can go to the right-hand side of the homepage where it says send us your voice message. So I'm pretty sure that's self-explanatory. As long as you've got a device, whether it's a tablet or a phone or a computer or a laptop or something that hasn't been invented yet with a microphone, you can send us your voice questions. Don't forget to tell us who you are, where you're from. We love to know where you're coming from, both literally and figuratively. So, yes, send us your questions. We are at the end of yet another episode, so thanks for joining us. And thank you, as always, Fred. It's a great pleasure.
Good to talk, and we'll speak again soon.
And good luck with the book launch.
Hey, next Monday.
There it is again, Space Warp. They're going to make it into a TV series.
Hope so, yeah.
Thanks, Fred. We'll catch you next week.
See you later. Bye-bye.
That's Fred Watson, astronomer at large, part of the team here at Space Nuts. And hello to Hugh in the studio. Hope you've solved that Rubik's Cube, which you've been working on for the last couple of weeks. And from me, Andrew Dunkley, thanks again for joining us. We'll look forward to your company on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.